Let's look at two more concepts related to the electromagnetic waves, and those are the Doppler effect and polarization. So let's first look at the Doppler effect. And if you remember the Doppler effect from sound waves, you know that there was a quite complex equation dealing with that. Well, with electromagnetic waves, it is a little bit different, and that's for various reasons. For one, electromagnetic waves do not need a medium through which to travel. With sound waves, we had to take into account the medium through which waves traveled and the speed relative to that medium. With electromagnetic waves, that is not a concern. And that is because we know that electromagnetic waves travel at the same speed in vacuum, the speed of light. And those speeds are really, really high compared to the speeds that we can attain by other means. So that means that only the relative motion between the source and observer is important when we're dealing with a Doppler effect. Here we have the equation for the Doppler effect. As I said, it's much simpler than what we dealt with for sound waves. So the frequency of the observer is frequency of the source times 1 plus or minus the relative speed between source and observer divided by the speed of light. And we assume here that the relative speed between source and observer is much smaller than the speed of light. Again, FO is the frequency perceived by the observer. Fs is the frequency emitted by the source. Now, there is a plus or minus sign there, and what that means is that when the observer and source come together, they approach one another, then we use the plus sign, and when the observer and the source move away from one another, then we use the negative sign. Remember with sound waves, we had to take into account whether the observer was stationary and the source was moving and what direction it was moving in and so on. Here, that doesn't matter. If the source is stationary and the observer is moving towards it, or if the observer is stationary and the source is moving towards it, the equation is the same. We take into account just whether they're coming closer together or moving farther apart. Now, the second topic for today is polarization. And since electromagnetic waves are transverse waves, they can be polarized. And what that means is that they can be made to vibrate along a single direction. That means that when the waves have their electric fields vibrating in a single direction, they become linearly polarized. Unpolarized light looks like this. So we have electric fields every which way. This is a beam of light that's coming towards us or moving away from us. So we're looking at it head on. And remember that with electromagnetic waves, there's an electric field component, and perpendicular to that, there would be a magnetic field component. But we are not concerned with a magnetic field. That's why I didn't draw it on here to complicate things even more. So we're just looking at the electric field and its orientation. And as I said, the orientation is just in all directions. Here we have polarized light. Now you see that there is only one direction chosen for the electric field. So essentially the electric field oscillates up and down like this as it is traveling through space. All of the other components of the electric fields are no longer there. So we can polarize unpolarized light. So we can make this unpolarized light polarized by passing it through a polarizer. So here we have the unpolarized light. It starts over here. We're placing a polarizer in front of it, and you can think of it as if there were just bars that this was trying to pass through. And it is pretty clear that the only component of the electric field here that is unimpeded, that goes straight through, is this one. So we get an electric field in this direction, so here is the polarized light. But remember that the electric field is a vector. So that means that we can project these electric fields onto the axis of polarization. So we're going to have a component here, and a component there, and a component here, and one there. So even these electric fields are going to have a component that is in that direction. So some of this light will pass through. The only one that doesn't is the one that is in this direction, because a horizontal vector does not have a vertical component. So that will not pass through, but all of the other orientations will have component in the direction of this polarizer. So then some of the light passes through. If we say that the original intensity, average intensity of the electromagnetic wave is I naught, then as it passes through the polarizer, half of the intensity makes it through. So when we start out with unpolarized light, passing it through a polarizer, we get half the intensity on the other side. Now, once we have polarized light with this intensity, we can pass it through an analyzer, and its purpose is to get light with its electromagnetic field oriented in a particular direction and with a specific intensity. So once we have polarized light, we can now play around with changing its intensity and also the orientation of the electric field. So this is what happens. Remember that the intensity is a function of the electric field squared, and we would have to basically project this electric field onto this axis of the analyzer and end up with polarized light on this side of the polarizer that has intensity, the previous intensity times cosine squared theta. What happened with the rest? Well, it got absorbed by the analyzer. So here we had the electric fields in the wrong directions, as it were, absorbed, and the magnetic fields as well. And here we just had part of this polarized beam absorbed by the analyzer. So we got this intensity, and the theta is the angle between this direction of polarization and this direction of polarization. So it's the angle between the original polarizer and the analyzer. This phenomenon was observed by a French engineer called Malleus, and this is now called Malleus' law. The fact that the intensity of a polarized beam that passes through an analyzer is the intensity before it had passed through the analyzer times cosine squared of the angle between the transmission axis between the analyzer and the original polarization of light.